Both physics and engineering are heavily reliant on problem solving. So in learning physics and engineering and studying it, what's also important is learning a problem solving process and practicing that process. So students at North Shore are expected to use a 5-step problem solving process. It's outlined in the guidelines for all work submitted in in-class teamwork, submitted as homework, as well as on the exams. That problem solving process is also outlined here, the 5 steps, what's being given, what is it that you need to find? What theory and analysis can you use? A solution process, or which we call solve, because that's the action that you're taking, and then a check. And I won't go over everything here, but I'll give you an example. You can pause if you want and make sure you read and understand what has to be represented in each of these 5 steps. Now, some people ask, do I need to label given, find, theory, and analysis? You don't need to, but it helps when you go back to look at your solutions and your homeworks to help you read it, to make it readable. In the given step, diagrams are also necessary. Sometimes it's difficult to know what the diagram is, but drawing something on there will help. And typically you want to clearly depict all those given information on the diagram. You want to make sure you use the proper notations. You want to make sure you use the units. When your theory and analysis, maybe at first you're coming up with a wrong theory. So it might not be, in this section, you might be doing a little bit of problem solving, a little bit of solving, but you might find out that you went on the wrong path, that something's missing, or in fact, the theories that you were trying to use would not be able to apply. So when you get to that final solving process, maybe you can start just plugging in numbers, but make sure your notations are correct. You can't just say anything is equal to anything else. Between equations, you can use the implies notation. If you get from one problem statement, that might imply the next one. If you're changing the form of your work, and then we'll work in the proper SI derived units. We won't have to work boil things back down to the SI base units. The check, in my mind, is the most important step. It's after you've completed the process. You want to make sure, is it complete? So things you can check, is the magnitude and numerical value reasonable? Is, plus or minus, does that make sense that you get a negative answer or a positive answer? That's sort of estimation. A unit check, are the units reasonable? A unit check using a dimensional analysis type in your check can be very important, and it's a good type of check. And what does it mean? What does it mean in terms of what you have learned as well? So that's the big key, that what did I learn from solving this problem? So let's take a look at an example. And this example is an experiment using a metal ball made of copper. And that in that experiment, it leaves the copper with a positive charge of 2 microcoulombs. Given the mass of the ball was 50 grams, we want to derive a fraction of the copper's electrons that were removed. And then we're additionally given information about that, which is really the theory that a copper atom has an atomic number of 29 and copper has an atomic mass of 63.5. So, what are we being given? We want to take that information and we want to convert it to variable form. So we have a ball, so the charge on that ball is given as 2.0 microcoulombs. So we can write that out. It's 2.00, so we know we have 3 significant digits here so our final answer will be rounded to 3 significant digits. Now it's a ball. There's not a whole lot we can do with a ball, right? We don't necessarily need to say that label this as Q, because we have this, but we can say, well, there's our ball, and it has that charge, and it's a ball, it's made of copper. And we know the unit for, the symbol for copper is Cu. So we also have the mass of the ball, so we can write that out. The mass of the ball, that's 50 grams. Now, do we need to convert that to kilograms? Because kilograms are base unit? Maybe, maybe not. Let's leave our given in this form, because if we have other things with grams, we won't have to convert it. And then we want to derive the fraction of the ball's copper electrons that were removed. So what does that really mean? So we want to know the fraction that's removed. So we want to know the number, we use n for number of, we can just use our subscripts to make this clear, electrons removed compared to when it was neutral, over the number of electron when we have a neutral. If I spelled neutral right, I always get U and E backwards. Spell check corrects me. Now, so we're also given this information, so clearly we're going to need it. We're given that the atomic number for copper is 29. So that atomic number, we typically write that's atoms per proton. So we typically, our atomic number uses a Z, I believe. So let's do Z of Cu. That's 29, and that's basically giving us the number of protons per atom. So if we weren't, really remembering this, it's physics 3. That might be more of a physics 2 thing, or chemistry. We can look it up. We've got the beauty of Google now as well to look up atomic number and know make sure we understand what is the correct variable that we use for atomic number. And then we have our atomic mass. Our atomic mass here is given as equal to, that's still copper, as 63.5. And atomic mass in this, it's given in grams per mole. So if those are going to cancel out, then we can just leave things in grams. We don't have to convert them to kilograms. So now we have, in fact, what we're given. And I'll just jump to the next page here where I've written that out a little bit more condensed so we can fit everything on the same page. So here's our given information, but we've also worked out what it was that we wanted to find, and we've worked through the first 2 steps. We really did that just by analyzing what was being said. But now we've got to do some theory. And how do we find this? How do we find the number of electrons removed from the ball? How do we find the electrons in a neutral ball? So when we're doing our theory analysis, we have to understand that number of electrons in the neutral ball is equal to the number of protons in the neutral ball. So that's our theory, right? If it's neutral, that means the charge is equal to 0. And the things that have charge in matter are electrons and protons. So we have the number of protons per atom. So we just need to determine what are the number of, total number of protons, right? Then we'll get the total number of electrons. So in doing that, here we have a protons. Maybe we don't have a formula because we're not studying this necessarily with a formula, but we could use a dimensional analysis approach. We want to end up with protons. We have protons per atom, so we need to get rid of atom. So we might need something else. We have a mole, and we know Avogadro's number is number of atoms per mole, right? So we need this Avogadro's number here, 6.02 times 10 to the 23 atoms per mole. We didn't realize it. It wasn't given to us, but in attempting a dimensional analysis, that's what came out. So we want grams per mole. That gives us a mole. Then we have atoms per mole, so the moles cancel. And then we have protons per atom, and we end up with our number of protons. So instead of using a theory here, what we used was our dimensional analysis. Now we could come up with the theory after the fact, and instead of trying to find a problem that does this exactly, and what we have is our mass divided by our molar mass, right? Mass divided by our molar mass times our Avogadro's constant times our atomic number, right? And that's what our formula, the formula that we ended up using to find the number of protons. So once we have that number of protons, we basically have the number of electrons here in the neutral ball. So now we have to work on finding the number of electrons removed from the ball. So we have the charge of the ball. If we divide that out, and it's positive, right? It's a positive charge, so that means electrons were removed. If it was a negative charge, electrons would be added to the ball. So we'd have a negative number of electrons removed, I suppose. But then we could just use the charge divided by the charge per electron, which we know that's the elementary charge. So we have the number of electrons in the neutral ball, that's the number of protons, the number of electrons removed from the ball, charge of the ball divided by the elementary charge. So here we did use this formula, right? Whoops. We use this formula in our analysis process. So that's what we call it, theory and analysis. So there's the formula, and then it might be better to work vertically. I'm working horizontally, so it fits on this page. But we substituted in exactly, so we can look for here. We have Q ball 2 times 10 to the negative 6. I didn't have to use 2.00. In the end, I'm going to round it to. This should say 2.00, right? But we'll check on that at the end. And then we can directly see that our elementary charge, we can check that here. Additionally, we could write, if we want, up here that we're using E is equal to 1.602 times 10 to the negative 19 Coulomb, and I'll use the symbology E minus for electron. So now we have a number for that. So basically, we're done with our analysis. We know what we want to find. We found these two numbers, so we can jump right to our solution process solving. We'll use the variables that we came up with in our find and plug into that formula, and we get our final result. We put a box around that. And it doesn't have any units. We have electrons removed divided by electrons, so electrons removed divided by electrons is unitless. Well, we're asked to find a fraction, so that fraction is not going to have the units. It's electron per electron, or electrons per electrons. So now we can check. So check. We talked about this at the beginning. The charge is positive, so the electrons have been removed. So the positive number on our solution is correct. We can go back through again with our dimensional analysis and verify that our units are correct. So, grams per gram, now that's per mole, so it brings mole up. So these moles end up canceling, and then the atoms cancel, and we end up with our units of proton. So we can do a unit check as well. But then further understanding what we have here, the number of electrons removed, if we look at this number, so it's good to calculate it, that's very large, 10 to the 13th, where but the total number of electrons being 10 to the 25th, on the order of 10 to the 25th, that's much larger. It's a factor of 10 to the 12th, larger than that. So our fraction is actually on the order of 10 to the 13th. So our fraction here, 10 to the negative 13th, that's very small. So if we were going to try to subtract out and determine how in fact many electrons were removed, we'd have a problem. We'd have to carry out 13 significant figures in order to get this number, right? So that's why we're looking for the fraction removed. And that's how we find the charge in the ball, number of electrons associated with that charge in the ball to begin with. All right, so that's it for this video, and hopefully that helps you understand the 5-step process.